Have you ever stopped to think about what people really mean when they say something is pure? I mean, we use that word all the time, but it doesn't always line up with what scientists mean, does it?
Right, like when you see something labeled as pure, you
Huh.
kind of assume it's just that one thing, nothing else added.
Exactly. But then you look closer, maybe check the ingredients, and you're like, wait a minute, there's a whole lot more going on here. And that's exactly what we're digging into today. We've been looking at some really cool stuff about this whole pure thing, like figure 2.1 from our source material.
Oh yeah, the one with all the everyday products, right?
Yeah, things like bottled water, cleaning products, all claiming to be pure. It got us thinking, what does pure even mean from a science perspective, and why should we care?
Well, the first thing to understand is that scientists have a much stricter definition of pure. It's not just about being unadulterated or natural. For a scientist, a pure substance means that every single tiny particle in that substance is exactly the same chemically.
So it's like every little building block is identical.
Exactly. And that's where the source material gets really interesting. It points out that most of the stuff we encounter in our daily lives, oceans, rocks, even the soil, aren't actually pure substances at all. They're what we call mixtures.
Ah, so that pure bottled water, which is mostly water molecules, that could fit the scientific definition, but something like pure orange juice, with all its sugars and vitamins, is definitely not scientifically pure.
Exactly. A mixture is simply when you combine two or more pure substances together. They don't chemically bond or anything, they're just physically mixed.
So like when you stir sugar into your coffee.
Exactly. The source gives another example, dissolving sodium chloride, table salt, in water. You can boil the water off, and the salt crystals are left behind. That's just a physical process separating the mixture, but the sodium chloride itself is still a pure substance.
So no matter how you separate a mixture, the pure substances within it retain their own unique identities.
Precisely. And another key characteristic of pure substances is that they always have the same properties, regardless of where they come from.
Makes sense. So salt is always salty, whether it's from the ocean or a salt mine.
Exactly. Now, when it comes to mixtures, things get a bit more complex.
That's where we get into the different types of mixtures, right? Homogeneous versus heterogeneous.
Right. The source uses a classroom activity, activity 2.1, to illustrate this.
Oh, yeah. Tell me about that.
So imagine a classroom divided into groups, each mixing different substances together. Some groups mix varying amounts of copper sulfate and water, while others use things like potassium permanganate or common salt.
Okay, and what happens?
Well, some of the groups, particularly those with the copper sulfate, end up with mixtures that look completely uniform, the same throughout. Those are homogeneous mixtures, also known as solutions. Think of sugar dissolving in water. It all looks the same, right?
Right, you can't see the individual sugar crystals anymore.
Exactly. And the source points out that even within these homogeneous mixtures, the composition can vary. Some groups might have made a pale blue copper sulfate solution, while others might have a much deeper, more intense blue.
So even though it looks the same throughout, the amount of stuff dissolved in the water can be different.
Precisely. Now, the other groups in the activity, those who mixed things like salt and iron filings, end up with mixtures that look visibly different in different parts.
You can see the separate components.
Exactly. Those are heterogeneous mixtures. Like oil and water, no matter how much you shake them, they'll always separate into distinct layers.
So homogeneous mixtures look the same throughout, while heterogeneous mixtures have visibly distinct
You
parts.
got it. Now, the source then focuses on a specific type of homogeneous mixture solutions.
Okay, solutions, like salt water, right?
That's one example. But what's cool is that solutions can exist in all three states of matter: solid, liquid, and gas.
Wait, really? A solid solution?
Absolutely. Metal alloys, like brass, are solid solutions. Brass is typically about 30% zinc and 70% copper, all blended together uniformly at the atomic level.
Wow, I never thought of it that way. And gaseous solutions.
The air we breathe is a prime example. It's a mixture of gases, primarily nitrogen and oxygen, all blended together homogeneously.
Mind blown. So solutions aren't just liquids, they can be solids or gases too.
That's right. And the source introduces two key terms when talking about solutions: the solvent and the solute.
Remind me what those are.
The solvent is the substance that does the dissolving, and it's usually present in a larger amount. Think of water and salt water. The solute is a substance that gets dissolved, usually present in a smaller amount, like the salt in salt water.
So when I make a cup of tea, the water is the solvent and the tea leaves are the solute.
Exactly. The source also provides some other examples. iodine dissolved in alcohol to make tincture of iodine, or carbon dioxide gas dissolved in water to make those fizzy drinks we all love.
So in soda, the gas is the solute. That's interesting.
Yep. And solutions have some pretty unique properties. First, as we already discussed, they're homogeneous, meaning they look uniform throughout. Second, the particles of the solute are incredibly small, less than 1 nanometer, which means they can't even be seen with a regular microscope.
So tiny.
And because they're so small, they don't scatter light. If you shine a beam of light through a solution, you won't see the path of the light.
Unlike, say, shining a light through a dusty room where you can see the beam clearly because of the dust particles.
Exactly. Another key property is that you can't separate the solute from the solvent using regular filtration. The particles are just too small to be caught by a filter. And finally, solutions are generally stable, meaning the solute particles don't settle out over time.
Okay, so stable, tiny particles, don't scatter light, can't be filtered. I'm getting a good picture of what a solution is.
Great. Now, another important concept related to solutions is concentration.
Concentration, that tells us how much solute is dissolved in a given amount of solvent, right? Like how strong the coffee is.
Precisely. The source introduces terms like dilute, concentrated, and saturated.
Dilute is weak, concentrated is strong, and saturated is when you can't dissolve any more solute, like when you add too much sugar to your tea and it just sits at the bottom.
Exactly. The amount of solute that can be dissolved in a solvent at a particular temperature to make a saturated solution is called its solubility. And different substances have different solubilities.
So you can dissolve way more sugar in water than you can salt, for instance.
Absolutely. The source even highlights an activity, activity 2.3, that demonstrates this difference in solubilities. They test salt, sugar, and barium chloride in water and find that they each dissolve to different extents.
That's a cool way to visualize it. And the source also gives us ways to actually calculate concentration, right?
Yes, it introduces 3 common methods: mass by mass percentage, mass by volume percentage, and volume by volume percentage. And it provides the formulas for each.
Math, my favorite.
It even gives a practical example, example 2.1, showing how to calculate the mass by mass percentage of a salt solution. In that example, 40 grams of salt dissolved in 320 grams of water results in an 11.1% mass by mass percentage.
Okay, so we've got the tools to measure just how concentrated our solutions are. Pretty handy.
Absolutely. Now let's shift gears and talk about those other types of mixtures, the heterogeneous ones.
The ones where you can actually see the different parts?
Exactly. First up, we have suspensions.
Suspensions, like muddy water.
That's a good example. The source defines a suspension as a heterogeneous mixture, where solid particles are dispersed throughout a liquid, but they don't actually dissolve.
So the particles are just floating around.
Right, and they're big enough to be seen with the naked eye. Think of shaking up a bottle of salad dressing. You can see the herbs and spices suspended in the oil.
Okay, so suspensions have visible particles. What else sets them apart from solutions?
Well, unlike solutions, suspensions scatter light. If you shine a beam of light through a suspension, you can see the path of the light because the particles are big enough to reflect it.
That's how you can see the beam of car headlights in fog, right? Because fog is a suspension of tiny water droplets in the air.
Precisely. Suspensions are also generally unstable. If you let a suspension sit undisturbed for a while, the particles will eventually settle to the bottom due to gravity.
Like when sand settles out of water.
Exactly. And because the particles are relatively large, you can usually separate them from the liquid by simple filtration.
So let it settle or filter it out. Easy peasy. Now, what about the third type of mixture? The one the source calls a colloidal solution, or just colloid.
Colloids are really fascinating. They're kind of like a hybrid between solutions and suspensions.
Hybrid? How so?
Well, they appear homogeneous, like solutions, because the particles are very small, but they're actually heterogeneous, like suspensions, because the particles are still distinct and don't truly dissolve.
So they trick us into thinking they're solutions.
In a way, yes. Milk is a classic example of a colloid. It looks smooth and uniform, but it's actually tiny droplets of fat dispersed throughout water.
So even though you can't see the individual particles, they're still separate entities.
That's right. And the source highlights a cool phenomenon associated with colloids, the Tyndall effect.
The Tyndall effect. What's that?
It's the scattering of light by colloidal particles. If you shine a beam of light through a colloid, you can see the path of the light, because the particles are large enough to scatter it.
Oh, like when sunlight streams through a foggy forest, you can see the beams of light because of the tiny water droplets in the fog.
Exactly. And the source points out that the Tyndall effect is what makes some air purifiers able to detect microscopic particles in the air.
So cool. Now, besides scattering light, what other properties do colloids have?
Well, like solutions, they're generally stable, meaning the particles don't settle out over time. But unlike solutions, you can't separate the particles by simple filtration because they're too small to be tracked by a filter. You need more specialized techniques like centrifugation, which spins the mixture at high speed to separate the components based on density.
Centrifugation, like in a washing machine spin cycle.
Similar concept, but much faster and more precise. And when talking about colloids, we use specific terms for the components.
Right, dispersed phase and dispersion medium. What are those again?
The dispersed phase is like the solute in a solution. It's the substance that's dispersed throughout the mixture in the form of tiny particles. The dispersion medium is like the solvent. It's the substance in which the dispersed phase is distributed.
So in milk, the fat droplets would be the dispersed phase and the water would be the dispersion medium.
You got it. And the source provides a handy table, Table 2.1, that shows various types of colloids based on the states of matter of the dispersed phase and the dispersion medium.
Cool. Like fog is a liquid dispersed in a gas, milk is a liquid dispersed in a liquid, and smoke is a solid dispersed in a gas.
Exactly. There's a whole variety of colloids out there. Now, shifting gears a bit, the source moves on to a really fundamental concept, the difference between physical and chemical changes.
This seems like a key distinction in understanding how matter behaves.
Absolutely. The source starts by defining physical properties as characteristics of a substance that you can observe without changing its chemical composition.
Yeah.
Things like color, hardness, melting point, boiling point, and density.
So basically how it looks and feels and behaves under different conditions.
Precisely. And a physical change is any change that alters these physical properties but doesn't change the substance itself chemically. For example, melting an ice cube is a physical change. The ice changes state from solid to liquid, but it's still water, HO.
So even though it looks different, it's still fundamentally the same substance.
Exactly. Now, chemical properties describe how a substance reacts with other substances.
Like how flammable it is or how it reacts with acids.
Exactly. Yeah. And a chemical change, also called a chemical reaction, is when a substance transforms into one or more new substances with different chemical compositions and properties.
So burning wood is a chemical change because the wood reacts with oxygen to produce ash, carbon dioxide, and water vapor, all new substances.
Exactly. And the source cleverly points out that burning a candle involves both physical and chemical changes.
Right, the wax melts, physical change, but it also burns, reacting with oxygen, chemical change.
Precisely. The source then challenges the reader, or in our case the listener, to classify some everyday changes as either physical or chemical.
Oh yeah, like cutting trees, melting butter, rusting iron, that kind of thing.
Right. And the key to determining whether a change is physical or chemical is to ask yourself whether new substances with different chemical properties are formed.
So cutting a tree is a physical change because it's still wood, but rusting iron is a chemical change because a new substance, rust, is formed.
Exactly. Now, moving on to the final section, the source delves into the two types of pure substances, elements and compounds.
Elements, those are like the basic building blocks of matter, right?
The source credits Robert Boyle with first using the term element in a modern scientific sense, and Antoine Lavoisier with providing a clear definition. An element is a pure substance that cannot be broken down into simpler substances by chemical means.
So it's the most fundamental form of a substance.
Precisely. And these elements are further classified into metals, nonmetals, and metalloids based on their properties.
Oh yeah, the periodic table.
Exactly. Metals are typically shiny, malleable, ductile, and good conductors of heat and electricity. Examples include gold, silver, copper, and iron.
And mercury is metal that's liquid at room temperature.
Correct. Nonmetals, on the other hand, are generally not shiny, malleable, or ductile, and they're poor conductors of heat and electricity. Examples include oxygen, nitrogen, carbon, and sulfur.
And metalloids are kind of in between.
Yes, they have properties that are intermediate between metals and nonmetals. Silicon, for instance, is a metalloid that's used extensively in electronics because it's a semiconductor.
Cool. And the source mentions that there are over 100 known elements, with 92 of them occurring naturally.
That's right. And most elements are solid at room temperature, 11 are gases, and only 2 are liquids, mercury and bromine.
It's amazing to think that everything in the universe is made up of combinations of these
It
elements.
really is. Now, the other type of pure substance is a compound.
Compounds, those are formed when two or more different elements combine chemically, right?
Exactly. And they combine in a fixed, specific proportion.
Mhm.
For example, water, H2O, always has 2 hydrogen atoms for every 1 oxygen atom.
And the properties of a compound are completely different from the properties of the individual elements that make it up, right?
Absolutely. Water, for instance, is a liquid at room temperature,
Hmm.
but hydrogen and oxygen are both gases.
So it's like the elements lose their individual identities when they form a compound.
In a way, yes.
Yep.
And the source uses an activity 2.4, to illustrate this difference between a mixture and a compound.
Tell me about that.
So in this activity, they use iron filings and sulfur powder. In one group, they simply mix the iron and sulfur together. That's a mixture. The iron is still magnetic, and if you add acid, you get hydrogen gas. But in another group, they heat the mixture of iron and sulfur, causing a chemical reaction.
And that forms a compound, right?
Yes, iron sulfide. And this compound has entirely different properties. It's no longer magnetic, and if you add acid, you get hydrogen sulfide gas, which has that characteristic rotten egg smell.
So the key takeaway is that in a mixture, the substances retain their individual properties, but in a compound, they combine to form something entirely new.
Precisely. And Table 2.2 in the source summarizes these key differences between mixtures and compounds. It's a really helpful comparison.
Awesome. This has been such a fascinating deep dive into the world of matter. We've explored the difference between the everyday use of the word pure and the scientific definition, delved into the different types of mixtures, and distinguished between physical and chemical changes.
And we've learned that everything around us is ultimately made up of elements and compounds.
It's mind-boggling to think about the complexity hidden within the seemingly simple things we encounter every day.
It really is. And I think this understanding of pure substances and mixtures gives us a whole new appreciation for the world around us.
Absolutely. So, to our listeners, here's a final thought to chew on. As you go about your day, try to identify examples of pure substances and the different types of mixtures you encounter. Notice their properties. Can you see individual components? Does a liquid seem to scatter light? Does anything settle out if left undisturbed?
And think about the changes that matter undergoes. Are they just physical changes, altering the appearance but not the substance itself? Or are they chemical changes, transforming one substance into another?
These simple observations and reflections can really deepen your understanding of the world at a molecular level.
And who knows, maybe this newfound knowledge will spark a lifelong curiosity about the fascinating world of chemistry.
Thanks for joining us on this deep dive. Until next time, stay curious.